Hello all, welcome to Geo 391 Computational Methods in the Earth and Environmental Sciences on March 8th, 2022. Today I'm gonna have to record a lecture as I'm traveling. And we're gonna talk about how we can calculate forecast uncertainties. So to do that, we gotta think about what a random variable is, how we talk about populations and samples, uncertainty of the population mean, and then the difference between parameter uncertainty and model forecast uncertainty. So I'm going to start off by discussing this idea of a random variable. So a random variable is basically any variable that we don't really know what the value is. And it has an unknown statistical distribution. So a variable with unknown statistical distribution. And these random variables have two things. One is this mythical thing, and that's called the population. All right, and this is the true distribution. And this is a mythical thing. In fact, if you're thinking about things in a Bayesian sense, it doesn't even exist. If you're thinking about it in a frequent sense, there is some true distribution. And it has if we somehow knew it, we would know a lot of stuff about this random variable, but we don't know the population. When we take measurements, we get a sample. And a sample is like a random draw. From the population. So an example of this is we've been working with, say, discharge out of the Lochsa watershed. And there's this idea that there is a single distribution, a population that describes like the true mean, for example, the true mean annual discharge out of the Lochsa distribution. There's a single known mean for that distribution and a single known measure of the dispersion or spread of the flow around that mean, and that's the population. But we don't know that. All we get is a year-to-year measurement, and so we get a sample from that population. So what we're going to do today is talk about how we deal with the uncertainty of any kind of a description of the sample statistics, given the fact that we don't know the true statistics, and then how that manifests itself when we try to use a statistical distribution as or a statistical measure as a model of expected flow. How the fact that we don't know what the true distribution is makes our model have uncertainty. So the first thing I want to do is talk about some terminology of random variables. So we've looked at some of these histogram plots. And the histogram plot is a sort of numerical or approximation of a probability density. Probability density. So if I was to, for example, have thousands of years of samples of annual flow out of the lock saw, and the climate wasn't changing and things were sort of the same distribution always, I would find that here is, for example, the discharge, the annual discharge. So here's an increasing value, and this is 0, a decreasing value. We would find that, and this is the probability of measuring or getting, seeing a total annual discharge. And what we would find if we did this for thousands and thousands of years, that we would see that this variable would follow a bell-shaped curve, which is, maybe some of you have seen this from statistics. And the idea is that there's some value here. In fact, for this distribution, it's the mean value, which is the center of this probability distribution. And at the mean value, we have the highest probability of observing this value of Q. So this is the mean. And it is a measure of the central moment, or the center of this distribution of probability for here annual discharge. All right, and it has the highest probability. So this is what we call the expected value. If we were to measure this, thousands of times, we would expect that most often the value is pretty close to the mean, because that's what my probability distribution says. It has the highest probability of occurring at the mean. So we call this the expected value. All right. And then we'd find that, some years are dry and some years are wet, and there's some measure of spread around the mean. We call that the dispersion around the mean. All right, and the classic measure of that is what we call the variance, or the standard deviation. All right, so psi is the standard deviation. Which is a measure of the spread of our observed values around the mean. All right, so if we don't have very much spread, then we have a very tight distribution, and we know the mean, all the values fall really close to the mean. But if we have a large spread, then we have a large spread of our values around the mean. And the mean isn't necessarily, we don't expect our values that we observe in a given year to be very close to the mean. So these two ideas, one is the mean, which is the center of the distribution, and the other is the standard deviation, or the spread of the values around the mean, allow us to think about what our sort of expected value is, and then how often we might, or how close we expect a given sample from a year to fall to our mean. So we as natural scientists, never get to know the true probability distribution. So we don't know what this bell curve looks like. We don't know what the population looks like. We only get a few years of samples. And as a result, we don't know what the true mean is. So when we have a data set, it is a sample from this population. All right. And we don't know what the true one is. And in fact, we can think of when we have a sample, the mean is a random variable in itself. We don't know what it is. We don't know what the true value is. All right, we know what we measure, but we don't know whether if we were to get measurements, let's say we're still talking about annual discharge out of the LOXA, we know that, you know, over the last 10 years, the mean has been this, but over the next 10 years, the mean might be different. And so we just don't know what the true value of the mean is. We only have a sample. All right. And so that brings up this idea that we don't even know what the true expected value is of our population. We have measurements, and we can create a histogram that approximates a probability density, and we can calculate our sample mean, but we don't know what that looks like with regards to the true mean. So we are interested in we want to characterize our uncertainty of the mean. Of the true mean. And we can do that with this measurement. So let's redraw that a plot now. This is the probability. All right, it's a similar bell curve. This is the probability. But now this is the variable here is the mean. It's not annual discharge, it's the mean of that annual discharge. And it follows some distribution, all right? And it has a bell shape, mostly. And this is the expected value of the mean, all right, mu naught. And there is some uncertainty or standard deviation of the mean. So this is the mean of the sample means, and this is the standard deviation of the sample means. All right, and so somewhere there's an expected value, which would be the closest thing we know to the true value of the mean. And as we get out and we measure sort of population means, sample means that are farther away from the central tendency of the sample mean, these become less likely. So these are less probable. And this is the most probable value. All All right, so in a perfect world, we could take lots and lots of samples. We could figure out what the central or the average mean is. And we could figure out the standard deviation of the sample mean. And we could create a distribution that maps out the probability of measuring a mean given a sample. And the point is, the farther away from this average value, the less likely or the less probable it is. All right, so we can characterize, the trick is to figure out how we characterize the uncertainty of what we think the mean is, given the fact that we're going to have, say, one sample. So for example, we've got 20 years of the annual discharge out of the LOXAW. This is a 20-year sample out of some unknown population. So what we want to do is calculate the standard error of the mean. And I'm going to call that SE underscore M for standard error of the mean. And this is a measure of our uncertainty. If we have one sample, what is our uncertainty that what we measure as the mean is close to the true mean? All right, there's a lot of stats in here we're going to gloss over, but the idea is that the standard error of the mean can be written out with some assumptions in this equation. It is equal to, approximately equal to, S over square root n, where S is my sample standard deviation. All right, so for example, the standard deviation of my 20 years of LOXAW discharge. And n is the number of samples. All right, how many times have I made an observation? So let's just look at this. So then the smaller my spread is around the mean, all right, then the smaller my uncertainty of the mean is. So if all the means, if I measured for, you know, a bunch of different years, and I always find the mean value to be very close to the same value, then I would expect that I don't have much uncertainty in knowing the true value of the mean. That makes sense. And then the other thing is, the bigger the number of samples, that means the denominator gets bigger, then the better I know the mean, then standard error gets smaller. So the tighter the distribution of the mean, the tighter the distribution of my observations, the better I know the mean. And the more observations I make, the better I know my mean. So this is a really important, fundamental equation that drives a lot of uncertainty analysis. If you've done hypothesis testing, regression testing, it's all about comparing a mean that we measure to this idea of the variance of the population and deciding how far out are we on this bell curve. All right, and do we have a mean that is appreciably different from another mean, for example. Okay, so there's an important distribution, the T distribution, that was invented partially by this guy named Student, last name Student. And it can be used to describe the uncertainty of the mean. All right, it is a hypothesized probability distribution for the mean from a bunch of different samples of the mean. All right. And the basic idea is that it characterizes the uncertainty of the mean given a sample. So the t-distribution can be used to as a population distribution population distribution for the mean. All right, so how does the sample mean deviate from the true mean? And we can use this t-distribution to calculate the uncertainty of the mean. And again, I'm going to gloss over a bunch of details, but conceptually, here's what happens. We have some, we have a population, or sorry, a sample. I'm gonna keep getting these confused. So we have a sample, right? And we measure, so for example, 20 years of uh-oh, computer has frozen.